In this video, we are going to see about antenna radiation mechanism. So, need for antennas, a device that can capture the big signal from the tower efficiently and effectively to boost it for the classroom. The problem statement is we need to design an antenna that receives a specific frequency with high sensitivity to overcome path losses. So, introduction. An antenna is defined as a transitional structure between free space and a guiding device. The guiding device, such as a transmission line or waveguide, transports electromagnetic energy from a source to the antenna. In the transmitting mode, the antenna transforms guided wave into radiated free space waves. In the receiving mode, the antenna captures energy from free space waves and transfers it to a receiver. The field regions of an antenna is given in this slide. Near field and far field are the antenna regions with distinct characteristics, where reactive near field is the region where electromagnetic energy is stored. The region where energy is radiated away is the radiative far field. Next, radiation mechanism. To create radiation, there must be a time-varying current or an acceleration or deceleration of charge. Radiation is not possible if a charge is stationary, as no current is created. If a charge moves with uniform velocity along a straight wire of infinite extent, it does not radiate. Radiation occurs when charges are accelerated or decelerated by curving, bending, or terminating a wire. Applying voltage across a two-conductor line creates an electric field between the conductors. Electric lines of force act on free electrons, forcing them to displace and create a current. This movement of charges generate a magnetic field. The creation of time-varying electric and magnetic fields forms electromagnetic waves that travel along the line. As a transmission line begins to flare, the fields radiated by the two wires no longer cancel each other. In a flat configuration, the fields from the two arms reinforce each other in most directions. This translation leads to the geometry of the widely used dipole antenna. The dipole is classified as a standing wave antenna due to its current pattern. In a small centered fed dipole, charges reaches a maximum during the first quarter of the period. Lines of force travel outwardly a radiational distance of lambda by 4 during this time. During the next quarter period, the original lines travels an additional lambda by 4 while opposite charges are induced at the conductor. As the net charge on the antenna becomes zero, the lines of force are forced to unite and form closed loops. Current on a thin wire is created by the movement of free electrons. In a lossless two-wire line, reflecting travel waves combine with incident wave to form a standing wave pattern. If the spacing between two wires is very small, the fields from each wire cancel and there is no net radiation. Radiation occurs individually from each wire due to the time-varying nature of the current and the termination of the wire. The types of antennas are shown in this slide. Wire dipole, loop, wire monopole, Yagi-Uda antenna, horn antenna, microstrip patch, slot antenna, parabolic reflector, corner reflectors are different types of antennas. This is the mind map given in this slide representing the characteristics of antenna. Role of the antenna. It gives wide coverage, broadcasting, mobile communication purposes, uses for satellite communication, and the It allows devices to move freely while communicating, enables communication without physical wires. The indivisible of the antenna is given. Disadvantages are interference, environmental sensitivity, polarization sensitivity, size constraints, bandwidth limits, and some efficiency losses. This slide represents the applications of antenna. It is used in radar systems, radio astronomy, navigating systems, remote sensing, and medical applications. Mind map for this video is given in this slide. Thank you.